Now we move on to traffic density. So basically, traffic density is being defined as K, and that is equivalent to N all over L. So traffic density in vehicles per unit distance, that is K, and N is the number of vehicles occupying some length of roadway at some specified time, and L is the length of the roadway. So this density actually can be related to individual spacing between successive vehicles that is measured from bumper to bumper. So the roadway length actually is equivalent to the summation of S of I, wherein our I is equivalent to 1 to N. So we have to take note that our S of I is the spacing of the ith vehicle, distance between vehicles I and I minus 1 that is measured actually from bumper to front bumper of the vehicle. And N refers to the number of measured vehicle spacing. And basically, our K here is equivalent now if we try to substitute the value for our L in our equation. So from the equation, K is equal to N all over L. So this is now equivalent to this value or this equation. So we can have this equation, N all over the summation of S of I for the traffic density. I is measured from 1 to N. This is our traffic density. Or simply we can have our K, our traffic density is equal to uh, 1 all over bar S. So we have to take note that time headway and spacing are referred to as microscopic measures because they describe characteristics specific to an individual pairs of vehicles within the traffic stream. However, measures that describe the traffic stream, such as flow, average speed, and density, are referred to as macroscopic measures. So as indicated by the preceding equations, the microscopic measures can be aggregated and related to macroscopic measures. And we have to take note that based on the definitions that was presented a while ago, so a simple identity provides that basic relationship among traffic flow, speed, and density. So that is, we can have our Q, which is our traffic flow, which is in vehicle per hour, that can be equivalent to U times K. So this will be our equation. So this is our flow, our Q. We have, this will be equivalent to speed, which is denoted by U, multiplied to our K, which is our density. So our speed here is, of course, is the space mean speed, which is typically in mile per hour, and our K, which is in density, that is basically in vehicle per mile. Now we have an examples for speed, flow, and density. Vehicle time, headways, and spacing were measured at a point along a highway from a single lane over the course of an hour. The average values were calculated as 2.5 second per vehicle for headway and 200 feet per vehicle for spacing. You have to calculate the average speed of the traffic. So basically, in order for us to calculate the average speed of the traffic, so we can have the relationship with our flow and density. So it has to be calculated from the headway and spacing data. So from the flow formula, Q is equal to, so you make use here, flow is equal to 1 all over T, wherein our 1 all over our headway, which is 2.5 second per vehicle. So that is our headway. So basically, if we're going to substitute now the value for the value here for our equation, So we can have 1 all over 2.5 second per vehicle. And if you try to substitute, simplify rather, you can have a value of 0.4 vehicle per second. Now we are going to have now the data that were collected for an hour. So the data that were collected for an hour will be, you have here Q times 3,600, which is, or just have to compute, since this is vehicle per second, so we convert that one to hours. So we have now the value of 1,440 vehicle per hour. Then for the density, denoted by K, so we simply have K is equal to 1 all over our value for spacing is 200 feet per vehicle. So therefore, our density is 0.005 vehicle per feet. So if we're trying to have, if we're going to have a spacing over 1 mile, so 1 mile actually is 55,280 feet. So we try to convert our feet to mile. So 1 mile is 5,280 feet. So we get now the density, which is equal to 26.4 vehicle per mile. For us to compute for the speed, so we have the relationship a while ago that Q is equal to Q times K. So from that relationship wherein we have Q is equal to U times K. So solving for our U, so we can have Q over K. So we simply have to substitute the value for Q and K that was computed, flow and density. So our speed now is equal to 54.5 miles per hour. Now for the average speed. So we can also identify the average speed since we have our headway, which is denoted by bar H, which has 2.5 second per vehicle, and our S, which has the spacing that is 200 feet per vehicle. So therefore, this is the average spacing, 200 feet per vehicle. If we try to substitute, we can have now the average speed of the traffic denoted by U. This is now referring to the average speed of the traffic. So we simply have to divide our average spacing value over our average headway. That is 200 over 2.5. So we get a value of 80 feet per second or 54.5 mile per hour. So a while ago, we're able to identify the relationship that we were able to define actually and identify the relationship for the measurement and calculation of traffic stream parameters. However, it is also very important, very significant and essential to understand the interaction of these individual macroscopic measures so that we can fully analyze the operational performance of the traffic stream. So now we are moving on. Our focus now is how we're going to have the model that describe the interaction of these traffic stream parameters. So now we move on to speed density model. So actually, for the speed density model, so this is the most intuitive starting point for developing a consistent, generalized traffic model to focus on the relationship between speed and density. So we now consider the section of a highway with only a single vehicle on it. So we're going to consider a highway with a single vehicle. So under this condition, the density will be very low and the driver will be able to travel freely at a speed close to the design speed of the highway. So of course, since we're trying to consider we're going to consider that the highway only have a single vehicle, so that single vehicle can travel, that vehicle or the driver can travel freely on that particular highway that is closest, the speed, they can travel freely with a speed that is closest to the design speed of the highway. So this speed is actually referred to as free flow speed because vehicle is not inhibited by the presence of other vehicles. So the speed that is being traveled by the single vehicle, which is close enough to the design speed of the highway, is what we call free flow speed. because it is a free flow speed since the driver has no inhibitions over the presence of other vehicle. So as more and more vehicle begin to use a section of the highway, the traffic density will increase and the average operating speed of the vehicles will decline from the free flow value as drivers slow to allow the maneuvers of other vehicles. So of course, as time passes by, there will be more vehicles that will be using the section of the highway. So basically, the traffic density on that section of the highway will increase and the average speed of the vehicle will decline. So basically, it will decline from free flow value as the driver. It will decline from the free flow value because the driver will slow down or will try to slow down as other vehicles that is present were going to maneuver. So eventually, the highway section will become so congested. It will be having a high density that the traffic will come to stop and u now is equal to 0, and the density will be determined by the length of the vehicles and the spaces that drivers leave between them. So the high density condition is referred to as jam density. So eventually, as there will be congestion on the section of the highway as more and more uh, vehicles will be using the highway, and the density now can be determined through the length of the vehicles and the spaces of the drivers leave between them. So the high density with high density condition that is now being referred to as jam density. So one possible representation of the process described is actually being denoted as the linear relationship. So such relationship actually can be expressed in terms of this equation wherein space mean speed is equal to free flow speed multiplied to 1 minus density all over jam density. So this is an illustration for a typical linear speed density relationship. So the advantage actually of using a linear representation of the speed density relationship is that it provides a basic insight into the relationship among traffic flow, speed, and density interaction without clouding these insights by the additional complexity that a nonlinear speed density relationship introduces. So it is important for us to take note that field studies have shown that the speed density relationship tends to be nonlinear at low densities and high densities with those that approaches to jam density. So the overall speed density relationship is a better representation by three relationship. Actually, number one, the nonlinear relationship at low density that has a speed slowly declining from free flow value. Number two, a linear relationship over the large medium density region. And number three, a nonlinear relationship near the jam density as the speed asymptotically approaches zero with increasing density. So we have to take note that we present only traffic stream models that are based on the assumption of a linear density relationship. So that's how density and speed are being related with each other. So we move on to flow density model. So for this one, we have a parabolic density model that can be obtained by substituting the equations. And then we can obtain this equation, which is Q is equal to u sub f multiplied to k minus k squared all over k sub j. So all terms were defined. Actually, we were able to define a while ago what are this q, what are the u, the k, and our k value. So we have to take note that the maximum flow rate, which is represented by q's of cup. So this is our maximum flow rate. So the maximum flow rate denoted by that. So actually represents the highest rate of traffic flow that the highway is capable of handling. And we can have our case, the value for our k sub cup. We have to take note of our free flow speed, our use of f. And if it is not equal to 0, we can have this equation. K sub cup is equal to k sub j all over 2. and we can have the value for use of cup, which has use of f all over 2 as we simplify this equation.